Okay, so good afternoon, ladies and gentlemen. So today I have a big pleasure to introduce Pavel Krejčí. I think there is no need to introduce too much. Pavel is best in mathematics, best friend, best in his thesis, our former director, and so on. And now he will give a talk about non-convex variation inequality in contact mechanics, please.
Okay, so thank you, Shaka, for your kind and exaggerated explanation. And so I was asked to say something of our research, and so I will report on something that we have been working together with colleagues from Graz and Rio within the framework of the Continuum project, but as you know, neither of the three cities is on the Danube, but nevertheless, so Danube is in the country. And so the contact mechanics. Before I get to contact mechanics, I would like to share with you my concern about dimensional reduction for elastoplastic bodies. This is something, when you take, this is very standard. When you prior Bernoulli beam or Timoshenko beam, you take a three-dimensional body where this is the one-dimensional object. I repeat exactly the procedure by Euler Bernoulli, but I get something else. And I would like to understand why. So I will start with the beam, how I derive the beam equation using the Euler Bernoulli assumptions. And I will try to convince you that although it is different from the Euler Bernoulli beam, it is still acceptable. So first, transverse elastoplastic oscillation. What would be elastoplastic? Euler Bernoulli is elastic, but we need the plasticity. So beam is okay. Everybody knows what is a beam. It's thin and long. So L is the length, B and H are the transverse coordinates, which are supposed to be small. H will be the measure of smallness. And now, what I would like to show that if I take, for example, the von Mises model of plasticity and apply it to the Euler Bernoulli dimensional reduction procedure, we do not observe a sharp transition between elasticity and plasticity, but a smooth one. And so the geometrical assumptions are 2 points on the x-axis move from the up and down. Perturbations are of the order of h cubed in y and z, and h to the power 4 in the x direction. And terms of order higher than h squared are omitted. No. Now there is another modeling assumption that eccentric layer. No, this is something. No, this is not an assumption. This is something that we observe. The eccentric layer is subject to larger deformations than the central layer. And we want to derive an evolution equation for the scalar quantity U, which describes the vertical displacement. Keeping only terms of the order of h squared at most. And I refer mainly to a paper from 2007. So this is a very long thing, but I have the impression that we have not been really able to transmit this this observation to the community. Now, okay. So this is what we believe to able to model. After deformation, near the boundary, the displacements are bigger, which means that near the boundary we reach the plasticity, the yield limit earlier. And then the bigger the curvature is, the more the plastic region propagates into the interior. Now, So what is the other so, as I said, the x-axis, the displacement is described by a function u of x and t, no dependence on one is. So it goes sits only up and down. Now, the next assumption is that the displacement at distance z, the fibers that are perpendicular to the x-axis in the referential state remain perpendicular. This is different from Timoshenko. In the Timoshenko model, he introduces the angle of inclination with respect to the norm. Euler Bergman assumed that the perpendicular fibers remain perpendicular, which means that the displacement at distance z is minus z after linearization, minus z ux. And then the straight tensor, the straight tensor, of course, the straight tensor, if this would be an accurate formula, the straight tensor will only contain the epsilon 1 element minus z uxx. But, and as I said, the displacement in the y and z direction are of the order h cubed. And if I differentiate with respect to y and z, they become h squared, so I have to take them into account. And then we compute it afterwards from the mechanical consideration. Now, consider two words. So epsilon elastic plus epsilon positive, there is nothing special. For the elastic components, we have the isotropic Hooke's law and the Ritland constant L. The yield criterion, the homogeneous yield criterion, the stress deviator, the norm of the stress deviator is less or equal than 2/3 of R squared. You will see in a moment why they put 3/2. 2/3, sorry. The admissible stress domain, this is the stresses satisfying the homogeneous yield criterion, and then the homogeneous flow rule says that. So there are three different ways, so to say, in principle equivalent ways to describe the flow rule, either that epsilon p dot belongs to the subdifferential, the indicator function of the R of sigma, or the dual formulation that sigma belongs to the subdifferential of the Minkowski function of the Kr star of epsilon p dot, or a variation inequality. This is my preferred. This is my preferred way to describe the flow rule in the form of a variation inequality. The Minkowski function of the dual set, this is what the people call energetic formulation. So this is so far the standard. Reduced constitutive box. Now, so again, the stresses of the order h squared from the elastostatic equilibrium equation divergence sigma equal to 0. We deduce that only sigma 1 component is of the order h squared. And now, as I said, we measure everything that is of the order bigger than h squared. Now, from Hooke's law, if the identity is sigma, so delta is the Kronecker sigma, right? The Kronecker density. So we have a relation between sigma, the sigma product with delta, and epsilon e with delta multiplied by 2 mu plus lambda, and this is our epsilon e, contains the two terms which you have to identify, which we don't know yet, but we can compute them from this identity. We compute epsilon e delta and plug it back to the constructive relation, and what we get is that epsilon e. Now the elastic tensor is epsilon e11 minus mu epsilon e11 minus mu epsilon e11. Mu is the Poisson ratio, and capital E is the Young modulus. And so this is the relation between Young modulus and Poisson ratio. This is where it comes from. So far everything is classical. And now the deviator. And now you see why we have 2/3 in front of the yield condition, that when it is really in terms of the one-dimensional setting, then the yield condition is nothing but E, the Young modulus, multiplied by the absolute value of epsilon E1. One is necessary for the R the yield level. And we have the flow rule. And the flow rule is, again, is the von Mises variation inequality rewritten for the 1D case. And now epsilon plastic plus epsilon elastic is epsilon, but epsilon is nothing but minus ZUXX. Very important. And now, so this is a variation inequality where minus ZUXX is the input and epsilon E, epsilon P are the output. So this is a very simple variation inequality which everybody can solve, including myself. This is the solution. So we have a given function epsilon. We want to decompose the function epsilon into the sum sigma plus xi. Sigma is less or equal than R, so R is our yield limit. And xi satisfies the variation inequality that we have seen on the previous. And this is the mapping which epsilon associates. Sigma is called the stop operand. And if we properly choose the initial condition, which means that there is no previous history in the evolution, then the stop operator has a scaling property. The stop operator applied to a constant c times epsilon is equal to c times the stop operator with threshold R over absolute value of c of epsilon c, positive or negative. Now, the constitutive, how does the constitutive equation for the elastoplastic beam looks like? Yeah. So you remember sigma 1 was the stop applied to minus EZ UX. But according to the scaling property, this is minus EZ, the stop with threshold R over E absolute value of Z. And so what can we say? So a distance Z from the x-axis, the longitudinal fiber behaves like an elastoplastic element with elasticity modulus Z and yield point R over capital EZ. Which means that eccentric fibers are higher in elasticity and weaker in plasticity. And now, but we have all the layers. We will integrate over the layers from minus Z to Z. So we have, and so we will take sums or integrals of stops. So this is one stop corresponding to one level Z. The green line is another stop. And some of the stops has a tendency to smoothen the transition from perfect elasticity to perfect plasticity. And so this is something that we can, for example, reconstruct the history of the, if we can measure the state across the profile, we can reconstruct the history of deformation. So this is, for example, this would be our input history. So it starts at some minus C, then goes up and then goes down again. And then the stop distribution of the stops here, depending on R. So this is a piecewise linear function with slopes -1, +1, -1, 0. And eventually, the stress distribution across the profile. Now, this is the z-axis, right? From 0 to h. You see that the stresses are not uniformly distributed. They depend on the history. So we can, to some extent, if we were able to measure the stresses across the profile, we can go back to the history. But not everything, because part of the history is erased, part of the history is conserved. Now the momentum bar. So X y Z is the geometric point of the beam, and this is the classical momentum balance in elasticity or elastoplasticity. And now our function u has a very special form. So we take the test functions u hat also of this, the same special form. What we get is this. The dynamic part utt times u hat is transformed into utt u hat plus h squared over 3u x pt u hat x. This is something that you don't see in the classic Euler-Bernoulli. I don't know, because it is of the order h squared. Okay, then the stress term. Look. So we integrate from minus h to h. V squared now appears. The stop, the thresholds are over the absolute value of z dz. We transform this in by substitution. We transform this integral into something. The steps is r, the weight function r to the minus 4, but we do not integrate from 0. This would not be integrable. We integrate from a value which is potentially very large because h is very small. And then the boundary condition is transformed into the right-hand side of the equation. And what we get? Yeah. No, first the method, which this is our mapping that associates with epsilon this integral over r. And if you this is a stress strain law, which is elastic until epsilon equal to r over eh. Then and the elasticity constant is E over 3. And so if h would go to infinity, then we would get the classical elastic law. And such an operator with superposition of the stops with some weight function, this is called the Cauchy-Shilsky operator. The distribution function. Gamma, our distribution function, gamma is now r to the minus 4 for large values of r, 0 for small values. So the zeros correspond to the elastic part of the graph, and the plastic part of the graph starts only when r is bigger than epsilon becomes bigger than r over e. And so this is not the equation that I would call the elastoplastic counterpart of the Euler-Bernoulli view. And you see that, so again, yeah. P is of the order 1 because the elasticity constant is independent of h. Right? So P is of the order 1. The stress part is of the order h squared, but this is also of the order h squared. So I don't see any reason why this should be neglected. Well, what is usually done in the Euler-Bernoulli. Yeah, so Euler-Bernoulli would have only utt and uxxxx. But when I do the domain dimension analysis, I think that this term should not be automatically cancelled. In particular, you will see that it plays an important role in further developments. So this would be our proposal how an elastoplastic beam or bending of an elastoplastic beam can be modeled. And the Cauchy-Shilsky operator has very nice properties. It satisfies the classical energy balance. So this is power supply to the system equal to the potential energy increase plus dissipation. The dissipation is positive in agreement with the second principle. And it has very nice monotonicity properties. It is monotone P of epsilon minus P epsilon hat. Tested with epsilon P minus epsilon P hat is greater or equal than the time derivative of something positive. And we have also. And yeah, so if we elect epsilon P equal to epsilon somehow, then we get the similar inequalities for the x derivative or the t derivative. I mean, in distributional sense. These integrals are not really differentiable in T. So we have to understand that integral from T1 to T2, etc. And there is another kind of monotonicity, namely that T epsilon T times epsilon T is positive. And so you can already imagine that solving equations of that type must be very easy because we have all the necessary analytical properties that are usually needed for solving a PDE. Now, the rail. So we imagine that the rail is the elastoplastic beam, essentially, which is, of course, you can discuss about, in particular, the plasticity. I will comment on the plasticity. But since it is not substantially simple to consider elastic beam, so I propose to do it immediately for the elastoplastic case. It costs nothing. So we imagine that the rail is something like a beam, and on the structure which is granular. So there is a granular foundation, and the beam is on the granular foundation, and there is a moving body train along the rail. And yeah, so this, you would probably not be happy if this really happens, right? But this is exaggerated, of course. And so, yeah, so there is on the one hand, there is the deformation of the structure, and there is the reduction of the empty space in the foundation. There is some empty space between the particles. The empty space decreases, and the particles may possibly break, which will be another parameter that we will call damage. So there is a change of the empty space, change of the displacement of the elastic displacement, and damage. Now this is okay. This is a trivial element. I think the picture is first on the train a bit. So this is the track in Mlčechosti. You asked me where Mlčechosti is, so
it looks straight.
Yes, and what is interesting that the rails meet there near Vranyany. I have not been in Vranyany, so I don't know whether they really meet or not. So you see the granular structure of the foundation and the rails are basically straight. Oh, but yeah, something like that could really happen. For example, if the foundation is subject to a long-term heavy load, then, or if there are some, I don't know, rain or some water.
Great floods could happen.
Sometimes the water can transport the grains out of the foundation, and then you can possibly, if you are particularly unlucky, witness behavior like that, but yeah, hopefully not. Now, and so what is we are coming closer to the contact problem. So yes, you understand the contact will be between the rail and the foundation. So the rail itself is an elastoplastic beam, and we describe the contact between the rail and the foundation as a contact problem. So this is the equation of the beam, and we have now, so G is a moving load, the train, and Q is the stress is a force produced, the force of reaction between the rail and the foundation. So rho is whatever parameter, mass density, elasticity modulus, and Q is the reaction of contact with the granular foundation, and G is the medium. Now, what is important is the energy balance. I insist on that we have to make sure that our system does not produce energy from nothing, although it would be nice to have another energy source, but this has not been observed in the reality yet. And so the energy balance is that the power supply to the system must be decomposed into a stored energy increase and dissipation rate. Dissipation rate has to be positive. And then, yeah, second principle of thermodynamics, dissipation rate has to be positive. And now, so what is the energy balance in our case? So this is clear. This is the kinetic energy. UT squared plus UTX squared multiplied by the corresponding factors. And then there is PUX, XUXST, and there is PUUT. So this is the power supplied to the elastoplastic machine, and this is the power supplied to the contact between the foundation and the rail. And we have to make sure that we are able to find some stored energy functionals which will guarantee that the dissipation is positive. And yes, stored energy, this is the stored potential energy. Now, we have to define the constitutive law between U, the displacement of the rail, and the force of contact in such a way that we would be able to find the function of W such that Q UT minus dW of U dt is greater or equal to 0 to dissipation. And to do that, then the stored energy now consists of kinetic energy plus potential energy, and this is the dissipative term, and this is now the power supply to the system. The power supply to the system through the train, passing back and forth. Now, yes, the line cycle, the empty space between the grains and the foundation, the ballast, and Eric Bauer, a member of our Danube team, he introduced a concept which is called void ratio of the granular material, which equals Y. So Y is the void ratio. S is subsidence, which means compression. And we also introduced the damage parameter W. And the admissible domain K of W, the state domain, is something which is above the hyperbola. So it's an infinite domain upward and infinite domain to the right, but the whole evolution takes place below the horizon to the y-axis. Yeah, and what is the motivation? No. So U is this set U is the input. So U is the displacement of the rail which pushes on the foundation. So it goes down. This is the gravity. And now, what if we are above the critical line, the line Sy equal to e to the minus 2w, the reaction is elastic. But then, when U reaches the critical value, the elasticity is lost, the void ratio starts decreasing, and the compression increases. This is why the admissible domain cannot be convex. If you want to let the process continue, the non-convexity is substantial. And now, we introduce the damage parameter. The damage, eventually, we will assume that the damage depends on the stress variation. So the bigger the stress variation is, the bigger the damage is. But if the damage is bigger, then the admissible domain becomes smaller. So for W hat bigger than W, the admissible domain, this is the dark green domain, is smaller. So it means that if it is more and more damage, it is less and less elastic, and the void ratio tends to 0, so it becomes hard, and this is not the desired situation, because if you put the ray on a hard foundation, then at high speed you will see oscillations and things like that. Resonance and very bad things. So the elasticity of these of the foundation is important. Now, contact rate. Yeah. So now, so in the first step, we assume that the function W describes damage, that it is a given function. Of course, it is not given. It will depend on the history. But for let us take first the situation. W is given, and U is given. And W star is some maximum value of the and the domain K, W is a star-shaped Alport regular set. So at each boundary point, there exists an outer tangent ball of radius. You can compute the radius, which is 2 to the e to the minus W hat, which is a fixed number. W star. And now, so our input is U, which is only 0 and U, so they always go down. This is the gravity. And eta is an element of the set W, and Xi is U minus eta, and we know that eta is orthogonal to the boundary. And it's because the domain is not convex. If the domain would be convex, we would have only this part in the variation inequality. But if it's non-convex, we have to add another component for non-convex R prox regular set. So this is 1 over 2R, right? So this is a variation inequality for non-convex R prox regular domains. So domains that are in an outer tangent. And there is a whole theory of that. People make a lot of computations about that. So the variation inequality is well posed in the sense that for every U, W, and W11, there exists a unique solution Y and S in W11. And in addition, if U and W1 is a bounded sequence in W11, and UN converge to U, W, and converge to W uniformly in the space of continuous functions, then the solutions are bounded in W11 and converge uniformly. So we even have continuity with respect to the supernorm, provided we are able to have bounds in W1. And now look again at the variation inequality. This is a rate-independent variation inequality, which means that the only space is where there is any hope for good continuity properties are spaces which are invariant with respect to time transformations, which is the subnorm and the W11 norm. So these are the only spaces that are of practical use when we work with rate-independent evolution. Some consequences. Yeah, if you think about the decomposition is not orthogonal in general. So C dot is normal to the boundary, but eta dot is not necessary because W changes. If W would be constant, then eta dot would be tangential. But if W changes, then eta dot is not normal, but eta dot plus is not tangential, so eta dot plus W dot eta yes, sharp, eta sharp, where eta sharp is again a time-dependent vector, is tangential. And then, so there are some, these are technical things. So if y and s belong to k of w, then 1 minus delta y s belong to k of w because it is star shaped. And so now we take this z, plug it into the variation inequality, divide by delta, then the quadratic term disappears because it contains another delta, and what remains is that c dot times y0 is greater or equal to 0, but there's nothing but y dot decreases, which means the void ratio decreases in agreement with natural expectations. The void ratio cannot increase. Now, granular materials are not extensive. So only compressive stresses can occur. And so the natural way would be to define the stress Q. So Q is the stress on the contact. So Q is something which is an elasticity modulus multiplied by the negative part of the substance, which I call S of W and U, an operator which with U and W associates Q. And which means that the stress is non-zero if S is negative, it is zero if S is positive. So it means if the contact is lost, there is no stress on the contact. The stress can be non-zero only if contact takes place. And now the energy extremes are again. So this is our variation inequality. Now we make another manipulation. We take z equal to 1 minus delta y s plus delta s minus. What we get is this inequality again divided by delta tends to 0, the quadratic term disappears. And what remains is the variation inequality of the time minus us. Minus is greater or equal than d by dt of something. This already looks like energy inequality. Indeed, if the elasticity modulus is a function of s minus squared plus y squared, then we get the energy balance which we wanted to have. So u dot times u greater or equal than something positive, which is our potential energy associated with the contact. So we have solved the problem of energy balance in this way. Now, and again, this is a very easy variation inequality. We can do all the manipulations again. Z equal to 1 minus delta, and divide by delta, let delta tend to 0. And we get something that looks like energy inequality, but without S minus. And now, if we prove that u dot of t is less or equal than a constant, then everything is bounded. And from the orthogonality of the normal tangential vectors, we get that if w dot is bounded, then eta dot is bounded, and that is still bounded. And in particular, q dot is bounded by a constant plus 1 plus w dot, and this constant is independent of w star, the curvature of the boundary. And yeah, this is of course the main point of the whole construction, and then what is the proof? The proof takes something like 15 pages. This is what we did with Giselle Montero, Vincenzo Recupero some 3 years ago. So this is very technical, but yeah. But this is, for example, a situation where this result is of some help. Lipschitz continuity of the solution mapping of the non-convex variational inequality. And so capital G is the function that describes the boundary, right? So G less or equal than 1, this is exactly the boundary of our admissible domain. And what we have is a local Lipschitz continuity in W1. So again, this is in rate-independent situations, there is no hope for any better norm than W11 because W11 is the natural norm for rate-independent evolutions. So even in 1D, if you have a one-dimensional variation inequality intervals, you do not have Lipschitz continuity with respect to any other norm but subnorm in W11. You still have continuity in W1P, but no Lipschitz condition in W1P for P bigger than 1, even in 1D. It's not a question of multi-dimension or whatever. So W11 is the natural space, is the only space where we can hope for this kind of regularity. Now, this, sorry, if we take U and W to be given, so U is the displacement induced by the HV for the moment we can assume to be given, and W is the damage which we also assume to be given for the moment. Now Y and S are the outputs of the solutions of the non-convex variational inequality with U and W given. Now, the reaction formation is elastic as long as Sy stays away from the boundary of W. This is what I already said. And now, for a given W, the stress limit value is a decreasing function of the one direction, but Y can only decrease during the process. So at constant W, the limit value of the displacement and at which irreversible compression starts increases as a result of the consolidation of the material. So the void ratio decreases, the material consolidates, provided we are able to keep the damage parameter constant. But we are not. We shall see that it does depend on the process. But this would be, in case we would have no damage, the material consolidates. This is, again, something that we would expect. So it's not the evolution of W is not independent of the state, but increases as a result of damage. And yeah, the final goal is to show that the model is well posed, even if the damage parameter depends on the history of the process, and it will depend on the stress variation, the stress on the contact line. No, so WXT is given, and we consider now the coupled system, the PDE. Now I remove the constants and the parameter H is constant anyway. So this is our PDE coupled with the variation inequality on the contact line with the given damage function W. And this is easy. So we calculate approximations, sines, cosines, and we test by we use the energy balance equation, the monotonicity of P is monotone, and so the Minty trick works. So this is very easy. This is something of the kind of basic course of PDs. Now, damage dependent. Now we take what happens if we take two different damage functions, W1, W2, we construct the corresponding solution. We know that the solutions are unique. And so Q is Qi now is S of Wi U. And now, so we subtract equations. U bar, Q bar are the differences, U1 minus U2, U1 minus U2, we test by U2. Now, this is monotone, this is nice. And so what we get is, we integrate the time, we get, from this we get UT bar squared, UTX bar squared. Now you see why it is important to keep the term here. We would not have UTX squared. If we had taken classical aerodynamic, we would not have it. And on the right hand side, we have Q bar U2 bar. Now, so we can forget about the pure kinetic terms, and we have this one, UTX squared, so we call it constant U1, because this is dominated by this. But we still have Q bar squared, which we don't like, because we do not know how our operators behave with respect to the L2 norm. So we have to reduce this to the L1 norm. So this can be replaced by the supremum over X squared, and this can be replaced by the supremum over X and T squared, but we can remove the square. So we remove the squares, and we have the supremum over X of UT bar is also equal to the supremum over X and tau of Q bar. Now this can be estimated from above by the integral from 0 to t Q bar sub t, which is still okay. So the stress is a function of the variables x and y and s, which for a given function w satisfy the variation inequality. So this is the variation inequality. Basically, this is the set k of w. W moves in time. Not a fixed point. No, and this is now the modeling assumption that W, the increment of the damage is proportional to the total variation of the stress. So the stress oscillations on the boundary increase the damage. And now, we define the set V of admissible stresses, which satisfy an inequality. Integral 0 to t from Q2 star also equal to the constant, and with some initial condition Q star. And then, of course, we take a function Q star. So we prescribe a stress. This Q is a stress. We prescribe a stress in V. We define the new damage to be a function of the stress variation. And then we solve the PDE. No, no. Maybe my time is over already.
Nie. Jo? Nic.
Nic.
Nic. Tam ti to taky nejde? Aha, tak that's really frozen. Now I can.
Aha.
Now I will sit here, yeah?
Aha. Okay, thank you. Okay, so we choose the fictitious value of the stress. We associate the damage with this stress. We solve the PDE problem, find Q as a solution of the PDE problem, and prove that Q is an element of W, and then prove that the mapping of Q star associates Q is a contraction. And then that's it. Okay, so we have here two U1, U2, U1, U2 are the solution of the PDE. U bar is again U1 minus U2, etc. And now W is also equal to W hat if W hat is chosen according to the set, the admissible set V. And U, T, and W are uniformly bounded independently of W. And we have now theorem 2. This is the Lipschitz continuity theorem for the non-convex variation inequality, which by the Grunwald argument can be written as U bar. This is different, like U1 minus U2, L1 norm, also equal to the integral U2 bar plus W2 bar. Well, W2 bar is smaller than Q2 the integral of U2 star, and UT is also bounded by that. So what we get is that the integral 0 to T of U2 bar is less or equal than the integral of the supremum of the integral 0 to tau U2 U bar T star. It's some constants which are independent, which depend only on the initial data and on Q, what was the train, the moving Q. Now, so we are in the situation, we have two functions, V and V star, and by easy manipulation, we prove that the mapping, which is V star associated V, is a contraction with respect to a specific norm, the norm e to the minus mt integral 0 to t, etc. So this is and so the mapping which is Q star associates Q is a contraction on the set, on the admissible set V of the stresses. So so we take a fictitious stress, we compute the stress from the equation, and we prove that the mapping which the stress star associates the stress is a contraction. And then there's this, and then you see that this is a norm which is compatible with the rate independence. Okay, and then this is the final result. So if W is defined as a total stress variation, then there exists a unique solution, because we have contraction. So we choose Q0 something, for example, something independent of time. By induction, we define Qi to be the mapping. T, this is the mapping which is given stress associates the new stress, right? And so we iterate, and T is a contraction, and T is a contraction in V. So Qi converges strongly, and then everything converges because all the operators are continuous. And the limit is I can say infinity of Ui. The solution is again unique because we have monotonicity and contraction. And so the Lipschitz continuity of the input output mapping generated by the solution of non-convex variation networks. This is what allows to set up this iteration procedure, and the successive approximations which converge. Yeah, and so another thing, variation inequalities, they have the advantage, they automatically produce the correct sign in the energy balance. Variation inequalities, this is just another interpretation of energy exchange. And so this is something that what would happen if the load moves periodically back and forth? So can we expect that somehow the foundation completely disintegrates, or that it becomes completely rigid? So both would be bad. So, and I don't know. It might be of interest to look at what happens for if the load is periodic. Okay. Simple example. Non-convex variation inequalities in continuum mechanics. I was talking about something similar in Pavel last month in a conference. This was a control conference and sweeping processes, and I mentioned that it is possible to combine non-convex sweeping processes with PD. So they also thought this, how can you do that? It's possible. And there are definitely other possibilities. I leave that to somebody else. I'm basically retired. I have no further motivation. And that's all. Thank you.